Alright, so the first thing I want to talk about here are the ideas of between group variation, within group variation, and their relation to this test statistic F. So the way I'm going to do that actually is in a slightly different format than usual, where I just want you to imagine this as like a number line where this end is sort of less perceived fairness, if we're talking about fairness of the police, and this is more perceived fairness. So the closer you are to this end of the line, the more fair you think the police are, and the closer you are to this end of the line, the less fair you think the police are. And we're going to say that we are looking at three different groups. So this group here, the squiggle group, we're going to call our urban group, who tend to see the police as relatively unfair. And this is roughly based on literature, but as usual, all numbers in these things are made up. So we'll say on this end of our fairness line, we'll say we have people who live in rural areas who tend to see the police as most fair. And in the middle here, we have people who live in suburban areas who tend to see the police as, somewhere in the middle. And on this page, as you'll see, it's kind of especially made up in terms of what the numbers are. But let's just say, for the sake of argument, that this is what the distribution looks like. So our urban folks are the squiggly lines, suburban folks are the straight lines, and rural folks are the zigzag lines. And we would say in this group, we have pretty high between group variation, because as you can see, if you were to kind of look at the average responses in these groups, they're all pretty far apart from each other. So we would say this is high between group variation. Because this group is really distinct from this group, which is really distinct from this group, and that's reflected in the fact that this one has a really low typical response, this group has a real sort of medium typical response, and this group has a really high typical response. We would also say that there is low within group variation. And within group variation refers to how similar the members of each group are to each other. So if these are three samples and we've plotted their responses on this line, we would say that all the responses for the urban group are pretty close together, all the responses for the suburban group are pretty close together, and all the responses for the rural group are pretty close together. But let's imagine another scenario now. So we have the same line, where we're plotting sort of perceived fairness of the police. And now let's say that our samples look like this. So our curly line is still our urban group, our straight line is still our suburban group, and our zigzag line is still our rural group. All right, so we have a slightly different situation here, right? Where if you look at so we got urban, suburban, and rural. So we'd say that across these groups, the average or typical response from each group is still pretty different from each other. So your average response for the urban group is still here, which is pretty much on the side of low perceptions of fairness. For the rural side, your average is over here, and that's pretty much still on the side of high perceptions of fairness. And our average response for our suburban group, which we could put around here, is still in the middle. So we could say that we still have pretty high between group variation. But something has changed here, and what's changed is that members of our groups are no longer that similar to each other. So within our group of urban respondents. We have, some people over here who would say the police are really unfair. We also have some people who are kind of more middling in their views. So we'd say that within each of these groups, and with suburban too, we've got some people who are sort of more on the less fair side, some people who are more on the more fair side, and the same kind of spread with the rural group too. And so what we'd be describing here is high within group variation. So we still have pretty distinct differences if we only focus on the means, but now we also have a pretty wide spread within each group. And just looking at these two, you might think to yourself, which one of these gives us the best evidence that urban, suburban, and rural residents have different views of police fairness? And I think most people would probably point to this one, right? So we have these three really distinct groups that are separate from each other and have really different sample means. Whereas in this group, we have different sample means, but the groups are just less distinct from each other. So part of what your analysis of variance test is doing is taking this into account. And it's sort of telling us whether our samples look more like this or more like this. But we're not done yet. So let's consider another scenario. So we have the same line here. So we have perceptions of fairness, and we have our groups here. Just using different kind of lines, again, to show what they are. And here we have our urban group, our suburban group, and our rural group. So this is urban, suburban, and rural. All right, so let's consider this situation now. So we've sampled people who live in all these different areas, and as you can see, we have the same overall pattern in terms of responses, where rural respondents perceive the police as most fair, suburban respondents are in the middle, and urban respondents perceive the police as least fair. But what's different here? Well, we don't have this situation, because we still have responses from each group clustered together, but now what's different is that the average responses from each group are pretty close together. And here you could say that urban, suburban, and rural respondents in this situation all have pretty similar views about police fairness. None of the groups would see the police as very unfair, none of the groups would see the police as very fair. Instead, they're all clustered in the middle. So we'd say that we have low between group variation. But unlike our second example, responses within each group are still clustered pretty tightly. So here we'd also say that we have low within group variation. So our differences between our samples are not that pronounced, whereas in both of these examples, our means are all spread far apart. Here, they're all clustered tightly together. But like in our first example, we have all our curly lines clustered together, all our straight lines clustered together, and all our zigzag lines clustered together. So in this case, which of these is a better set of samples to demonstrate that people in urban, suburban, and rural areas have different views about the police? Well, you'd probably point to this one again, because here the samples are more distinct from each other, whereas here they're more clustered together, even though the within group variation, so how far apart each of the lines are within each sample, is pretty low like it is here. All right, so we have one more way that this could go, thinking about your differences between samples and within samples. And we're going to be looking at our same line here, where we have less fairness and more fairness. And now I want you to imagine that you take these three samples, your urban sample looks like this, your suburban sample looks like this, and your rural sample looks, oh, my lines are getting not that distinct either. And your rural sample looks like this. So we still have 3 sets of lines. We still have our urban sample of curlicue lines, we still have our suburban sample of straight lines, and we still have our rural sample of zigzag lines. But now what do you see? Well, drop my pen. For our urban sample, our suburban sample, and our rural sample, we still have different means. And they're not as far apart from each other as they were in either of these examples, but they're still different from each other. They are all more clustered in the middle, though. But we also have a pretty big spread across each of them, which means that there's a lot of overlap between our samples. And in this case, you look at this, and just at a glance, it would be really hard to tell that your urban sample is distinct from your suburban sample, which is distinct from your rural sample. And in this case, what you'd be looking at would be a situation where you have low between group differences. So, and I probably could have drawn this as even more overlapping, but you have all your means are sort of towards the center of this line, and you also have a big spread within each sample. So you have high within group variation. And so if I zoom out here and we take a look at all of these situations, you can see that if you were to, have this not be blurry, if you were to take samples that had these characteristics, this one would give you the best evidence that you had drawn these samples from populations with different means. So this shows the clearest differences between your samples, where you have high between group variation and low within group variation. These two both give you some evidence that there's differences, but it's a little bit harder to see, because here there's more spread within each sample, and here there's not enough spread between your samples. And then this one is just kind of a mess of lines where you've got them spread out across each other and not that distinct in terms of their means. So as I said on the last slide, these mean squares between and mean squares within group describe what's going on here. So your mean squares between describes the extent to which your means are distinct from each other. Your mean square within describes the extent to which your different observations in each sample are clustered together, in each sample. When you have high between group variation and low within group variation like this, you end up with a high F statistic. That's not the right word. Statistic. Oh, hang on. Okay, you end up with a high F statistic. And the F statistic, like I said, is going to be our test statistic for this hypothesis test. But for now, I'm just going to go through each of these and talk about what you get. So a high F statistic is something you get when you have high between group variation and low within group variation. And so a high F statistic describes a situation like this, where you have multiple groups that are really distinct from each other, both in terms of how far apart their means are and how much variation there is within each group. In the next two situations, you have lower F statistics. So the way it's calculated, when you have high between group variation and high within group variation, it comes out to a lower F statistic. And a lower F statistic can describe either of these scenarios, where you have some evidence of difference, but here the groups aren't as distinct because they're spread out within them, and then here the groups aren't as distinct because even though there's less spread within them, there is not a lot of spread between them. So both of these result in a lower F statistic. Our last group here has the lowest F statistic, where when you have a situation like this, where you have low between group variation and high within group variation, you end up with a very, very low number for your F statistic. And it describes a situation where it's really, really hard to distinguish between your three groups based on the samples that you have. So the analysis of variance test is going to be a hypothesis test based on this F statistic. But I think it's really helpful at first when thinking about the F statistic is just to think about what it's describing. So the higher your F statistic is, the more your samples look like this. The lower your F statistic is, the more likely it is that your samples look like any of these three scenarios. And just to add on to this, I've been drawing it as a number line with different shaped lines here because I think that's helpful in visualizing it. But what's really going on here, if you want to think about this in terms of the sort of distributions that we've been seeing, is that you have a sample distribution that looks like this, this, and this, that are all distinct from each other. Here you have a sample distribution that looks like this, sample distribution that looks like this, and a sample distribution that looks like this, where they're distinct but spread out. You know, here we've got sample distributions that are tightly clustered together. And then here we've got sample distributions that just have, you know, a ton of spread and overlap, where it's really just hard to kind of tell where any difference is between them. So again, this would be like if you took a sample, you know, plotted all your responses. Here you'd have three very different, distinct sample distributions, and then in all these other situations, they're less different and less distinct, like what you can see in the number lines here. All right, so what do we do with this F statistic? And where does it come from? So now to talk a little bit more specifically about the F statistic. The F statistic is a test statistic, as I said, that's based on these measures of variation between groups and variation within groups. So your MS between, I said, is a measure of between group variation and when you hear between group variation, you want to think differences between sample means. So you want to think sample means that are very far apart from each other. We also have a measure of variation within groups, which we refer to as MS within, or your mean squares within groups. And there are formulas for calculating both of these. This is not something I have you do by hand in this class, again, because I think you really just don't get a whole lot out of doing this by hand. But if you're ever really, really bored, or really, really curious, or both, you know, look them up. Or don't. I don't know what I'm talking about. I always say dumb stuff like that when I'm like 20 minutes into a video and then I just can't do anything about it, so, you know, bear with me. Alright, so we've got our mean squares between groups and our mean square within groups, which are measures that are calculated from sample statistics, so calculated from the sample means, number of samples that you have, sample standard deviation, stuff like that, to come up with numbers that describe the extent to which the samples are distinct in terms of their sample means being different, which is your mean squares between, or the extent to which your samples are characterized by observations that are clustered tightly together. So here we have low within group variation, so this would be a low MS within statistic, and a high MS between statistic. Where again, each of these situations that I went through is described by different combinations of your MS between and your MS within. Where this is high MS between, low MS within, best evidence that these two things are distinct, and then here we have different combinations and less good evidence that your groups are distinct. The F statistic is calculated from these two numbers. And specifically, it's calculated by just dividing your mean squares between value by your mean square within value. So you'll have two different values for these, and when I go through an example, you'll see that as well. And you get your f-statistic by dividing them. So the fact that you're dividing them takes into account the fact that different combinations of these give you different good evidence. But the higher your between score value is, because it's on the numerator, the bigger your f-statistic is going to be, and the bigger your within squares value is, the smaller your f-statistic is going to be because you're dividing by it. So that's just sort of going through the equation and, you know, what the division means, but that part's not as important to know. What I do want you to know is that the f-statistic is plotted on something called an f-distribution. And an f-distribution is similar to a normal distribution. It's similar to a t-distribution in that it is a standardized sampling distribution. And what this means is that it's a distribution of possible sample values. In this case, the sample value itself is the f-statistic that you would calculate based on these things, and the probability of getting each one. Now, an f-distribution is a little bit different from the others in that it's skewed, so it's right skewed, it has a longer tail going out to the right, and most of your possible and likely values on the left, and it actually starts at 0, so you can't have any negative f values. If you get a negative value for f, you need to check your math because something has gone wrong. But otherwise, you have different possible f-statistics plotted along the bottom, starting with 0 and getting higher and higher, and the probability of getting each one. And the exact shape of the distribution, similar to the t-distribution, depends on the number of samples you have and the sizes of those samples. So really, it's a family of distributions like the t-distributions. But for the most part, they have this shape here of being a right-skewed distribution. It starts at 0. And it's a sampling distribution, which means that it's reflective of a world in which the null hypothesis is true. So it's your sampling distribution if the null hypothesis is true. So in this way, it's exactly the same as the t-distributions we've been looking at, where we're saying we are using this distribution to describe what you would get if the null hypothesis is true. If you remember way back to the slides like 20 minutes ago, the null hypothesis here is that all of your sample means are exactly the same. So what this is telling us is that if all your sample means are exactly the same, it's likely that you're going to get a pretty low f value, because if they're all the same, when you take samples, they're going to be pretty indistinct. So you're going to get a low value here. It's where the bulk of your distribution is, because if all your means are the same, you know, what are the chances that you're going to get sample means that look like this? And sample means that look like this are described by a high f-statistic, and they're really, really unlikely if it were true that people in urban areas, suburban areas, and rural areas all had the same exact attitudes towards the police. So what's the chance that if all the means really were the same, you would just happen to get people who live in urban areas who think the police are unfair, people who live in suburban areas who think the police are sort of middle fair, and then people who live in rural areas who think that the police are really fair. You know, if everybody had the exact same views about the police, it's really, really unlikely that your samples would just sort of sort out that way by themselves. So that unlikeliness is described by your high f-statistic, and you can see that in this tail here, whereas your f-statistic gets higher, it becomes less and less likely, because this is describing our probabilities. So also, as with our t-distribution, you plot your sample F statistic on the distribution. So let's say you get a sample F statistic and it's plotted here. You can then use this distribution to find your p-value, where in this case the p-value reflects the probability of getting a sample F statistic as large as the one you got or larger if the null hypothesis is true and that all of the populations you're looking at have exactly the same mean. So your p-value is the probability of getting an F statistic as large or larger than yours if the null hypothesis is true. And again, what that reflects is that if it's true that all the populations have the exact same mean, it's really unlikely you're going to pull out 3 samples that have really, really distinct groupings and means like this. And this gives you a high F value, which is unlikely. So now that you have met the F statistic, you've met your mean squares between, your mean squares within, and the F distribution, we're going to go back to the PowerPoint and talk about the analysis of variance test that uses all these things to test the hypothesis that all of your populations have the same mean.